Hello, everyone. My name is Jay Singh, and I will be your host for this NASA Ames Technology Transfer Program webinar on the various mission control, robotics, automation, and control technologies from NASA Ames Research Center. And I thank you for out of your day to attend this webinar. The webinar will be structured in a lightning talk format. The presenter will have 10 minutes to present their technologies and then 5 minutes for Q&A. Before we get started, I wanted to mention the Technology Transfer Program has over 1,000 patented technologies across the entire agencies, and NASA Ames Research Center has 100 different technologies available for license. I'd also like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them in the Q&A box, and we will answer them during the Q&A session at the end of the presentation. So at this point, I'm going to turn it over to our first presenter, John. John, take it away.
Thank you so much, Jay. Thanks for everybody who is joining us today. Really excited to have this opportunity to present this work, and I know Krishna and the other presenters are as well. Hopefully, Jay, everybody is able to see my screen now.
Yep, everything's good.
Okay, great. So thank you so much again. My name is John Melton. I'm a senior engineer here in the Systems Analysis Office at NASA Ames. I come from a long background of aerospace engineering, specifically kind of vehicle-oriented engineering in all different speed ranges. And I'm happy today to present some recent work that we've done that we call Maestro. And it's a system that we think will provide onboard wind estimations for safe and efficient low altitude urban flight operations. As aerial operations move more and more into urban areas, we know that there will be some new challenges that are going to arise. Our cities are dynamic and they're constantly changing, and that is complicated when vehicles need to fly at low altitudes where those building shapes will influence the wind. We have the additional challenge of knowing precisely where those vehicles are, because your GNSS, your GPS signals can be somewhat unreliable at times due to multipath reflections, diffusion, and potentially spoofing. And we know about the winds and how troublesome they can be in an urban canyon. Now, the smaller the vehicle is, the less inertia it has, and sometimes limits also on control power. Size, weight, and power can somewhat constrain what we can do on board with our sensors and our computing. But the winds are terrifically important for safe operations. They affect stability, trajectory, airspeed, etc. And so this research is targeted at looking at how we can improve operational safety and productivity for low altitude urban operations. So our system is entitled Maestro, and that's an acronym for Machine Learning Estimations for Urban Operations. It's a combination of some kind of low, what we call swap, size, weight, and power sensors with wind models and deep learning neural networks to provide onboard real-time estimates of the local winds. Now, Maestro not only makes those estimates exactly at the vehicle's location, but what's unique about it is that it makes those estimations over the entire survey area of the vehicle's sensors. And so we're initially focusing on LiDAR, and the LiDARs that we're looking at have a range right now out to around 250 meters. So these estimates will cover the entire 360 degrees that surround the vehicle, and we feel those could be extremely useful in determining safe and efficient traversal paths between waypoints. So how do we train this neural network on Maestro? And this slide gives you a little bit of some of the behind the scenes of what we're doing. On the left, you see a picture of a fully synthetic urban environment where we've run a computational fluid dynamics or CFD simulation to make an estimate for the winds around those buildings. And what we're going to do in this synthetic environment, and you can kind of see it, it's a little bit hard, the orange dots here on the left side of the screen, those are locations at which we're going to generate two pieces of data. The first is going to be the synthetic LiDAR image. And as many of you, I'm sure, know, LiDAR essentially gives you kind of a depth map. It tells you the distance to the hard surfaces that are around you. It does it in a full 360 degrees and plus or minus 30 degrees in elevation. So at each of those orange points, we're going to generate that synthetic LiDAR data, and we're also going to extract the wind field that surrounds that orange dot. And that's illustrated here in the rightmost column. So for every LiDAR location, there's also an associated wind field. And what we're going to train our neural network to do is to make that association between what the LiDAR sees and what the associated wind field is. So here on my next slide is our 5 examples from the training data and the evaluation data. So again, the left side here is 5 samples, 5 sample LiDAR images. The column in green labeled CFD is the exact solution that we've extracted from the CFD simulation for that urban site. The column labeled neural network, NN, there is after we've trained the neural network, we're comparing that with the exact CFD answer. And honestly, if you squint a little bit, it's kind of hard to differentiate the two. Now, of course, the real test in any machine learning is to see how your system performs on data that it hasn't seen during the training. And that's what I'm showing in the blue box here. So again, I've chosen 5 random locations here. You see the exact answer in the CFD column. That's what we know the system should be producing. The image in the neural net column is what the neural net actually produced. It took us about an overnight session on just kind of a commodity laptop when we first did this. But what's really exciting about it is that the evaluations for these type of networks can happen, as many of you know, kind of lightning fast. And as a matter of fact, these were taking less than 5/100ths of a second. So you could easily imagine a system that's operating at 20 hertz ish, providing these type of estimates to the path planning system on the vehicle for surrounding wind estimates. And that's going to be really critical as the vehicles descend below the surrounding building heights. So in summary, Maestro is kind of really focused on what I call these mean plus building urban winds. So mean meaning the mesoscale and the atmospheric boundary layer winds and the effects that the buildings have. Now, what we're currently not making estimations using Maestro for the gusts and turbulence that happen at higher frequencies. We're kind of trying to provide a good average of where the wakes are and where high velocity shear areas may occur based on what our onboard sensor, and in this case it's a LiDAR, is seeing. And we think that these wind estimates will be extremely useful for the path planning that has to occur to get to what I call the next waypoint. Ideally, these estimates will minimize the risk of collision with buildings, overloading controls. Maybe there's some special payload constraints that you're worried about in terms of accelerations. And it should help you make better power and energy estimates so that you have a better idea of how much energy it's actually going to take to go to that next waypoint in your trajectory. Where does Maestro fit in the guidance and navigation control stream? This is kind of on the left where we see that. Sensor A here could be the LiDAR. Sensor B could be a set of IR cameras that are also giving you the temperature distribution of your environment. They could be 3D visual cameras. There are a lot of sensors that could eventually provide this type of information to a deep learning neural network and help it improve its ability to make estimates of the local winds. Those wind estimates would be used along with the position and attitude information that's coming from the IMU by the path planner, which would then say, hey, autopilot, to get to that next waypoint, we recommend going this path because of what we're seeing in the winds. This work is being sponsored by a part of NASA's Aeronautics Research Mission Directorate that's called Convergent Aeronautics Solutions. It's kind of a modeled around kind of a skunk works type of operation, lean, fast, quick demonstrations. So over the next 2 years, we're going to be focused on taking Maestro from the purely simulation world and putting it on some hardware and going out and comparing the estimates that the Maestro system would make against measured local winds. How do we see Maestro being used in the package delivery and air taxi scenario? You could imagine receiving a flight plan and a mission forecast at the start. You'd update your onboard neural network as appropriate based on your destination and the weather. During the flight to your destination, you're going to be comparing and fine-tuning those estimates. And then as you descend to the lower altitudes and below building heights, you would rely on Maestro to make those wind estimates of the surrounding wind fields. Then upon return, background retraining of the network and continued updates with additional synthesis of data from other flights that are happening in the area, other field measurements, continuing set of simulations that you might be generating and synthetic environments, etc. We also envision scenarios where Maestro could be useful to both the DoD and other EMS providers. One thing could be assisting in landing on the fantail of a ship or assisting precision GPS guided airdrops. And finally, the prediction of urban plumes. We do have a recent patent on this. I think Jay and company can provide you additional information about that. And again, thank you so much for your time today. And Jay, I think I'm happy to answer some questions.
Yeah, John, thank you so much. That was very illuminating, very interesting use of that technology. So we do have a few questions. The first one is, so the LiDAR sees dust particles to create such images and get a vector field from the data. Is that something like how that works?
No, that's not how Maestro works. Unfortunately, both atmospheric LiDAR and the kind of hard surface LiDAR that Maestro is using both go by that same name of LiDAR. In
Got it.
our case, we're using kind of an automotive LiDAR, like a Google autonomous vehicle would use. In that case, there's a rotating array of laser beams that are sent out, and you do measure the time of flight of that signal, but from that you can then determine your distance to the solid objects. So again, think of it more as providing this depth map of your surroundings. It is not doing direct measurement of aerosols like an atmospheric LiDAR does. Those systems are still large garbage can sized and definitely not currently available for use on the smaller aerial robotics platforms.
Got it. Thank you. And, you're still sharing your screen, just by the
Okay, so let me stop sharing. There we go.
Right. So the next question is, which network was trained? Was it the convolutional neural network?
Yes, it was. Now, that's still an area that we're going to be researching here over the next year and a half. There are some specialties of doing convolutional neural networks, especially for the type of imagery that we're expecting to take in, that we think are probably a little more appropriate. Again, we're also this year primarily focusing on just processing our LiDAR data, but one could easily imagine, again, the importance of, let's say, also adding in some IR imagery, understanding the temperature distribution of your surroundings. There are many things that impact local winds and local weather. And so the more sensors you bring into this that are still lightweight enough to be considered to be practical to put on an air taxi or a drone delivery vehicle, the more information you can gather, the better.
Yeah. So I think this goes into the kind of another question. So how does Maestro take into account the wind speed and direction over the buildings? Are there other inputs besides the depth map? And so that just kind of depends on the amount of sensors you have, right?
Correct. Now, and there's a lot that goes on behind the scenes in the training. We train for all 360 degrees of onset wind direction, and there's let's just say there's some additional work that is done there in order to make sure that you're kind of aligned with that that higher altitude above the building height predominant wind flow direction. But so you do have to have some idea of that predominant wind flow direction. You're going to know that as the vehicle is traversing, above the height of the surrounding buildings. You'll have good wind estimations available there before you begin to descend below building height.
Got it. And so for kind of the sake of time, we'll ask two more questions. They kind of feed off each other. The first one is, so basically what you're doing is you train the model with LiDAR and offline CFD simulation data, and then predict the field based on the new LiDAR images. Is that
Correct.
right? So is the
Correct.
training data from the CFD model?
Correct.
Got it. And then the last one would be, is the example of the 12 hours of training time the amount of time it took to collect the physical data, or
That,
yeah.
that was me just training on my kind of clunky government issued Windows laptop. Um, and little optimism on a non-GPU laptop as well, by the way.
Oh, wow.
Yeah.
That's actually pretty good. Well, great. Thank you so much. And for the remaining questions, we can reach out to John via email, and we can get back to the people who asked the questions. Thank you again, John. That was very very fascinating.
Thanks for the opportunity.
And next up, we have Kalmanji, who will be talking about adaptive wind estimation for small unmanned aerial systems using motion data. Take it away.
Okay, good afternoon, everyone. Thanks for joining this seminar today. My name is Kalmanji Krishna Kumar. My co-author is Varam Stepanyan. Interestingly, this research that led to this patent, John Melton was also part of our team. So we came up with two different ideas. And it does, in some ways, maybe the same task, but in a very different level of the need-based, I would say, requirements. So let me talk about the adaptive wind estimation technology that we came up with. One thing I want to say is this work that we did was, I would say, almost 5 years ago. So it just shows that it takes a long cycle time to get to a level where we can patent it and so on. So I don't have fancy graphics which we used to have before, but I put together a couple of simple charts to hit on the technology and some of the benefits. So one of the challenges we faced right away when we started working on a project called Safe 50 that is trying to fly below the clutter, that is below the tree levels. And some of the demos that I went to, it was obvious that many vehicles cannot fly if there's a very good wind that's typically available in many parts of the country. And we don't have any control over them. On top of that, we also realized that many of these low-cost vehicles do not have a way to estimate the wind. So we came up with a simple technology. Our focus was trying to keep it simple so you can put it on the computer resources that are on the vehicle, and also using sensors that are already on the vehicle. So our sensors need, the minimum is the IMU, which includes the attitudes and the accelerations. That's all we need. And if we have other inputs like the electric current that's going into the motors and so on, we can improve our estimation quite a bit. But at the minimum, we need the motion sensing, which is the attitudes and the accelerations. One of the reasons we patented this was the technology is adaptive. So the estimation actually is attempts, and mathematically we have shown that it converges to the actual wind. And to do that, we also compute or estimate aerodynamic drag components. So all of this is done in real time as the vehicle is flying. And the estimates then can be used very effectively in trajectory generation and the inner loop control to keep the vehicle steady. So again, I want to emphasize it's a fast and reliable convergence to the theoretical true values, and it's adaptive, and it can be it's a very simple software actually, and uses onboard sensors that are typically available. This picture here shows a typical control diagram that anyone everywhere is using for autonomous vehicles. You have a planner that takes waypoints, and the key is to generate the trajectory that's flyable. And for that, you need to understand the wind. So that's the whole idea of coming up with the estimation. Now, moving to the next slide. I don't know why. Okay, here we go. So the applications we started out was one small UAS, like the DJI that was shown earlier. We also have tested on bigger vehicles. Currently, we are testing them. When I say testing, they're all in simulation. We are testing them on the big UAM type vehicles that NASA has certain designs. So it is equally applicable to both small drones as well as the bigger autonomous vehicles that eventually will be flying as air taxis. One of the ideas that people have talked about, and we think it's possible now with the cheap software running on all of the vehicles, will be crowdsourced micro-weather estimates, so that if you have really a traffic that we envision of the future air taxi business or UAM, AAM type environment, then we can use weather estimates or the wind estimates from each vehicle and do a crowdsourced micro weather, just like you do crowdsourced traffic for road vehicles. We are also in another project looking at distributed sensing, how we can have wind sensors that are part of the infrastructure in the city, augment that with this onboard sensing to get a better estimate for the whole urban environment. So this application, like I said, the biggest benefit we were going after was the drones we were using didn't have much computing power. So we had to make sure the software is compact and we get a really lightweight, low cost, because the methods are computationally very effective and can be easily implemented on conventional onboard computers. The power consumption is whatever the avionics is consuming, much less than that. And it does provide a fast and reliable estimation and theoretically shown to converge. We have not really done any actual flight with the software in the wind that we can go validate the system, but we have done a lot of simulations to validate them. I'm going to stop here and see if there are any questions.
Yeah, thank you. We had one question. Are the sensors inertial or other?
Yeah, they are inertial. Whatever the IMU provides, all are inertial. And that's why we have to estimate the aerodynamic drag coefficient before we can estimate the wind, because wind is aerodynamic wind with respect to the air mass. But the sensors are all right from the IMU inertial sensors.
And then how many sensors are on the like how many sensors do you need?
Oh, these almost all drones come with the 12-axis sensors, what they're called. They have magnetic compass. They have the 3 accelerometers. They have, some of them have 3 GPS. Then they have the attitudes and the rates. So yeah, I mean, pretty much all of the states of the vehicle. Now, if you want more sophistication, we'll have to go for sensors that estimate the current needed to run the propellers and so on. We can get better estimates as we have more sensors on board. But the minimum is what comes with a typical drone package. We are not tested on really small hobby drones like the one for photography and stuff like that. We are not. The scale that we are talking about is 55-pound, like a DJI, Metris, or the old S1000s and so on. That's the, I would say, the minimum requirement. Below that, we are not tested it. Sorry.
Yeah, no, that's very interesting. Thank you for that information. That's I think maybe a lot of people are going to start off on kind of those, entry level drones. So a couple more questions. Sorry. Are there any papers published regarding this work? And then there's just a couple more questions after that.
Oh yeah, definitely. If you search our names that's listed in the presentation, or even my name, and say NASA Ames, you will see in scholar.google.com. you will see the papers published.
Fantastic. So 2 questions here. How will this integrate into ADSB, and what are you basing your cost function on?
ADSB, I mean, ADSB is, as far as I know, it's an out signal. And we don't need ADSB because IMUs give all of the information. After I answer this, I'm going to see if Varam is online, if he can also add to it. And the second question, sorry, what was the second part of it?
What are you basing your cost function on?
The cost function. I think that's part of the technology, but I would say that it is an weighted error of the trajectory estimates and the actual trajectory. So, Varam, do you have more specificity to that answer? I don't know if you're online. I don't know if you can even turn your mic on, but I'll wait and see if Varam can talk to this or. Okay, maybe he's part of the, he came in as a part of the audience, maybe he can't.
Yeah, he might have, yeah.
You used the, yeah. So, but the bottom line is it's minimizing the trajectory errors that what we compute. And there may be other constraints posed. So it may be, it's all in the paper. So I would leave it at that.
Got it. And then we, for the sake of time, we'll just answer a couple more questions. How do you consider the distributed, how do you consider distributed sensing? Are you using multi-UAV or single UAV, but many sample points? Can you talk about that a little bit more?
It's actually a research we're just starting. And I can get answers to you exactly. I'm not involved in it, but I know that they are actually talking about putting sensors in some parts of San Francisco Metro, but it's not a research that's been done. So it's in the planning stages, but I can get that answer later to whoever asked that question. I don't have the real actual answer for that.
Sure. And then would it be possible to add sensors to gauge air quality?
No, I don't know the answer for that.
Okay, yeah, no worries.
Yeah.
If you are not using wind tunnel data for calibration, do you need specific flight trajectories or maneuvers in order to estimate the wind afterwards?
Yeah, so that's a very good question. Interestingly, since the wind, we are assuming there is wind, so there is a disturbance. So that there is always a perturbation. What we need is a perturbation from the intended trajectory. So if everything is perfect, our estimates will be pretty not good. So the assumption is there is wind and turbulence, which you're going to get anyway in a metro area. So the planned trajectory will never be sufficiently accurate to the executed trajectory. So you will get error. So our whole optimization, online adaptation is driven by that error. So I think that's not a problem once you say you're flying in urban areas with, there'll always be some kind of a disturbance.
Oh, okay, got it. Yeah, thank you. And for the remaining questions that have not been answered, we can get back to everyone with those answers. So thank you again. Thank you for the very fascinating talk.
Thank you.
And next up, we have Nan Nguyen, who will be talking about optimal control modification. Perfect.
Thanks, Jay. Good afternoon, everyone. So this presentation is about the work that I worked back in the 2008. It's been a long time, but anyway, I'm pleased to share this work with the audience. Jake, will you go next slide? So I don't know how many people online are familiar with adaptive control. So I put together a few slides to motivate this topic. So maybe that's kind of redundant, but I'm going to go through them very quickly. So adaptive control is viewed as an enabler for vehicle autonomy. So in particular, when we talk about adaptive control, we want to focus on the ability to do adaptation through closed loop control and mission management. So you can also do outer loop control, outer loop adaptive control. So both inner loop and outer loop can be made adaptable. So adaptive control is a technology that enables that adaptation, and it can integrate with vehicle physical hardware and software, and then it can also interact with other systems like human-machine interaction. So I draw this autonomy level chart, scale from low level autonomy all the way to very high level autonomy. At the very top is decision making and autonomy. At the bottom, you have adaptive control and guidance. So things that happen really quickly, and we want to be able to adapt if system go off nominal. Okay, so we have over the year applied adaptive control to many flight vehicles. So we want to show some of the work that we've done. Next slide, please. So just to motivate this topic, we want to talk about system uncertainty and why it is important to consider system uncertainty in aerospace vehicle operation and design. So, and all autonomous systems are subject to uncertainty because there are no such physical system that have zero uncertainty. So system uncertainty can degrade the performance and stability of autonomous system. And basically, uncertainties are things that we don't know about the system. It's the unknowns, right? We may try to do the best of our ability to capture that unknown through system modeling, but we can never eliminate system uncertainty. It's always present. However, we can manage the system uncertainty. So the way we manage system uncertainty is through modeling. So we want to model the system behavior so that we can capture many unknowns. And sometimes we cannot capture all of the unknowns. And then we apply safety factor or safety margin on top of the design. And then we also, restrict the operation envelope. So all those things are way that we can manage the system uncertainty. Okay. So if you look at the figure on the right, that is the flight envelope. So flight envelope is a way to restrict the flight operation to address system uncertainty, because outside of that flight envelope, the system is unknown. Okay. So next slide, please. And then we have uncertainty that's beyond the ability for us to manage. Things that happen once in a lifetime, or maybe something happened in a very rare event, but it does happen, like weather, flying into a downwash or something like that, structural failure. And so many things can happen that we could not anticipate and we could not even model. So how do we manage such uncertainties? And this is where adaptive control can come into play. It can offer the possibility for risk mitigation of system uncertainty. Next slide, please. So what is adaptive control, basically? So the definition of adaptation is it is the ability to adjust to changing environment through learning and adopting new behaviors to cope with changes. So the key word is learning and adopting. So the essential elements of an adaptive controller is a reference model, as shown in that figure on this chart right here. The reference model encodes the ideal behavior of the system. And then you got the error signal between the system response and the reference model. And then you have an adaptive law that adjusts the system dynamics to accommodate the uncertainty using that error signal. So it is a way to mimic the biological system, the concept of learning that enables system to adapt to changing environment, essentially. So the adaptive control provides a learning mechanism to internally adjust the system parameter so as it to suppress any undesired response due to uncertainty, and also to seek the optimality or optimal behaviors over a long time horizon. So next slide, please. So, this work that we did on optimal control modification is called OCM, was developed back in 2008 at Ames. So it underwent extensive verification and validation through piloted simulation study at Ames in 2009. So we did a lot of piloted sim study at Ames in the advanced concept flight simulator, which is shown in that figure, the lower right figure. You can show the cabin of the ACFS flight simulator. And we have 8 test pilots from NASA, Armstrong and Ames, participate in the study. And we had 7 different controllers, and the pilots flew these controllers inside the ACFS, and then they provided Cooper-Hopper ratings, which is a handling quality rating, and the optimal control modification received the most favorable rating from these pilots. And one of the key comments that these pilots provided was that the OCM, or the optimal control modification, is much more predictable than the other controller. So that in their view, predictability is a highly desirable attribute of an adaptive control. And then subsequently, we were able to conduct a flight test experiment on a NASA F-18 aircraft at Armstrong in 2010, 2011 timeframe. And that's a picture of the aircraft, the tail number 853, which is the F-18 aircraft at Armstrong that flew the optimal control modification. Next slide, please. So what are the features of the optimal control modification? So adaptive control really boils down to a mathematical process. So it is described by a mathematical relationship. So it's given by that particular equation there. That equation actually allow the controller to estimate the system uncertainty and then feed the system uncertainty back into the closed loop control to cancel out the uncertainty. So thereby eliminating the disturbance due to the uncertainty. Okay, and it's one of the key features of the OCM is that it enables fast learning or adaptation without sacrificing robustness. And if you look at some of the conventional methods, like the standard model reference adaptive control, it does increase performance by fast adaptation, but by the same token, it's also compromises or loses the robustness. So the performance gain is offset by the loss of robustness. Okay, so this figure on this chart can illustrate the difference between the optimal control modification and the conventional methods. I draw a ball there. The ball represents like a hypersphere. Okay, at the origin, we have 0 error. The error is between the reference model and the system response. Typically, conventional method wants to go to the origin, meaning that there's no error. Okay, but that's where the weakness of the conventional methods are, because by going to the origin, it ends up losing a lot of robustness. I mean that it cannot tolerate any sort of uncertainty in the system, and the closed loop system can go unstable. The OCM, the optimal control modification, it does not go to the origin, but instead it goes close to the origin, so it stay away from that hypersphere by small radius delta. And so in doing so, it trades performance for robustness. Okay, and you can adjust the trade-off by adjusting that delta parameter. Okay, and the cost function at the top, which is to minimize the error norm of that radius, is what led to the optimal control modification. So the optimal control modification does produce an optimal policy because it minimizes that cost function. The second feature of the optimal control modification is that it demonstrates a linear closed loop behavior under fast learning or fast adaptation. So why is it important? Well, linear behavior is much more predictable than nonlinear behavior. And therefore, it tends to be more preferred by pilots because the pilot that flew in that flight simulator, they commented that they liked the predictability of the optimal control modification. And that's why linear behavior provides better predictability, and perhaps that's what he saw. A lot of the conventional methods exhibit closed loop nonlinear behavior. So the closed loop system is nonlinear, and any nonlinear behavior is highly unpredictable. We don't know what to expect. And then the third feature is the ability to suppress persistent excitation input. So what does it mean by persistent excitation? So any learning system, online learning system, does require input, and that input must be persistently exciting or persistent excitation so that the parameter would converge with that persistent excitation input. But by providing that persistent excitation input for learning, it can also cause undesired system response because basically you're applying signal to the system and the system get excited by that input, and that is highly undesirable. So for the optimal control modification, it provides a damping mechanism proportional to the persistent excitation input. So the more persistent excitation input that you put into the system, the more damping you get. If you look at the equation, the box there, I show the two terms that represent the persistent excitation input. So that is a persistent excitation input. So whenever you put in a lot of signal, the signal would be converted to damping. And damping means that the system oscillatory response will be suppressed. So therefore, that provides a better response, a system response with the persistent excitation input. So those are the key features of the optimal control modification. Go to the next slide, please. Now, I don't know if you can play this video because I email you, but you can press. So this is the video that was, this is the flight test at Armstrong. And you can see the chase airplane behind there. And then the F-18 is flying in the front. And, that's how they typically do the flight test. They got the chase aircraft behind taking photo or video. Anyway, just a short video clip. And I think that's all I want to say about optimal control modification.
Thank you so much. That was very interesting. Let me get to the Q&As here. See if I can find. Yes. Okay. This might be for you. Sorry, the little all over the place with the questions. The Army's Future Vertical Lift Cross-Functional Team is working with several organizations to develop scalable control interface and facilitate autonomy in unmanned systems. Are you aware of their work, and are you collaborating with them for your work to be complementary?
Well, I mean, we definitely would be interested in any collaboration, but we're not aware of this activity. But we definitely would welcome any additional information and perhaps some discussion to explore potential collaboration.
Got it. How do you control security around this technology?
When you say it's control security, you're talking about like communication, data security, that kind of stuff.
Yeah, that's what I'm assuming.
Like hacking. Well, I mean, that's go without saying. I mean, adaptive control is a very, I would say, it tend to be sensitive, right? Sensitive in the sense, I'm not talking about security per se, but I'm talking about it is very touchy. If you don't know how to tune the parameter, then it may not work. And if, let's say, that the system can be hacked, and then people go in there and start messing anything up, potentially could cause some, catastrophic failure too, And I think it can go, it can apply to any control system, not just only adaptive control, but could be just a standard PID, anything like that, because a closed loop system is very sensitive to this, to any kind of fault injected into the system by security breach, right? You have some security breach, people go into the software and start putting in bad parameters. No, bad thing can happen to all systems, not just only, this particular control design, control technology.
Yeah, that makes sense. I got one last question here. Did you use OCM to adapt estimated aircraft parameters, or to adapt gains, or both?
Well, what they did in the F-18 test was that they created a bad model, okay? So they used the so-called dynamic inversion controller, which is a Boeing proprietary controller, and inside that controller, there are a bunch of parameters that represent aircraft aerodynamic coefficients, and the good inversion controller has the correct parameter. So when they did the test, they purposely messed up some of the aerodynamic parameter, like CM alpha, for example, which is the static pitch stability. And then they let the pilot fly to see if the adaptive control can regain the performance and matches the performance of the ideal system, with the original dynamic inversion controller, and they were able to regain the performance even with the bad dynamic inversion controller in the loop.
Yeah. And then we have one final question. The adaptive control requires very fast data collection plus responsive action. What's the requirement? 5 milliseconds, 500 milliseconds?
Well, yeah. So the faster you can get, that means that you can increase the gain, the gain. Then the faster the convergence you can also achieve. The parameter conversion depends on the adaptive gain. So the adaptive gain is also depend on the sampling frequency. So because you do a kind of discrete time controller design. So you could increase the sampling frequency, and then you apply a pretty high gain. And because this particular adaptive controller tend to be robust under the fast learning or fast adaptation, which means a high gain. So then we use a larger sampling rate. I don't know, I don't remember exactly what the frequency we use for the sampling for the F-18 flight test, but I think it pretty much easily, probably 100 hertz or something like that, perhaps.
Hi, thank you. And for the remaining questions, we will get those answered and send them back out to you. So thank you again, Nan. Appreciate it. Thank you for the very fascinating talk.
Okay. Thank you.
Yeah. And now we're just going to go over a quick presentation of how you can license these technologies, how you can use them for your own products and for your own company and things like that. Let me just share that. All right, I am assuming everyone can see that pretty well. So again, thank you everyone who showed up and took part of the webinar. Now I'm just going to kind of go over what the technology transfer program is and how you can leverage NASA technology for your company. So the NASA Technology Transfer Program has is all throughout the 10 different NASA centers. We're here in NASA Ames Research Center, and each different center has their own specialty. Ours, for example, here at NASA Ames, are things like autonomy and robotics, as you saw today, biology and astrobiology, cost-effective space missions, and things like re-entry systems. So that's just a few of the things that we're experts in. But let's say if you want something in propulsion, you can go to a different NASA center for that. But everything can be found at technology.nasa.gov. That's where all of our 1,000+ patents are hosted. So since its inception over 50 years ago, the NASA Technology Transfer Program ensures that innovations developed for exploration and discovery are broadly available to the public, trying to maximize the benefit to the nation. And so one of the things that is always asked is, why should a company license NASA technology? It's kind of like, why reinvent the wheel when we already created it and you can just use it? A NASA license allows access to technology for testing, to implement into a system, service, or product that could result in sales. The Ames Technology Transfer Office cares about success of commercial businesses, of course, and the negotiation of terms of these licenses is done on a case-by-case basis. And here's just some quick things that were worked within NASA Ames and now are out in the public. One thing is anti-icing formulas. You could put that on train tracks that was created for a NASA mission. So that helps prevent train delays, and it's also on airplanes. When you see like airplanes getting de-iced, kind of the formulation of that was at NASA Ames. And the one on the right, the mineral analyzer, it's a X-ray diffraction technology that's on the Mars Curiosity rover. And what it does is it drills into the soil, grabs the soil, shakes it really quickly, uses X-ray diffraction to see what the contents are. And so what that does is, like, let's say here on Earth, you can, rather than taking the sample and sending it to a lab, you can find out the components of that soil right then and there, rather than having a long lead time. So now I'm just going to kind of go through how you can get to those technologies. So the main portal is technology.nasa.gov. You can go through the search bar, which is the magnifying glass search icon, and you can also go through the patent portfolio. So one of the things you can do through the search is do keywords, see what's something that fits what you want. But if you just want a general understanding of what technologies we have, kind of the best way is go through the patent portfolio. So once you click on the patent portfolio, you'll be greeted with different technologies categories that we have. We have everything from communications, aerospace, optics, medicine, biotech, manufacturing, all across the board. And today was a robotics one, so that would be under the robotics category. So for today's walkthrough, we'll go through the instrumentation category. So once you click on the instrumentation, you'll be greeted with this page, and there's different technologies that will come up. And so let's click on the read more button on the real-time radiation monitoring using nanotechnology. Once you click on that, you'll be greeted with this tops page, which is called a technology overview preview page. And if you have any questions on the technology, you can click on the questions tab. But this gives you an overview of the technology, why it was created, what the benefits are, what the applications are, as well as it's a link to its patent. And if you want to download this fact sheet to take it on the go, just click on the download fact sheet as PDF, and it gives you the same thing that was there before, but in a more readable format, I would say, and which allows you to share it with other people as well. So it's very important to look at the patent number and what is claimed within the patent. So once you click on the patent number, just make sure it matches up. And then it's very important to look at the claims and the description, because that's what you will be working with for the patent. You will be practicing the art of the patent through its claims and its description. And ways to understand how to apply for a license is you can go under the resource tab and click how to license, or you can just click on apply for a license on the page of the technology you're interested in. And again, one thing I want to reiterate is your company must be legally formed in order to apply for the technology. And if you're an international company, you must have a US company form. So these are just a quick rundown of the 3 types of licensing agreements we have. We have an evaluation license, which allows you to kind of test run the technology and see if it fits your business and your development goals. And those cost structures are tiered at different levels, and you can see that at the How to License webpage. This is kind of just a good way to be like, hey, maybe this technology will be good, maybe it won't be. Let's test run it. Let's see if we have the capabilities to produce it. It's a very, very popular license type. The second one we have is a startup license. And so with the startup license, there's no upfront costs for commercial use of our technology. And so we're letting companies kind of hold on to their cash while they're securing the intellectual property needed to carve out competitive marketplace. One thing with the evaluation license is that you cannot commercialize the technology. It's just more to understand if it works for your needs. But with the startup license and then your standard commercial license, you can take those technologies and commercialize it and hopefully get revenue and royalties or revenue for that. And with both the startup and commercial, and even with the evaluation license, but not so much, you need a full business plan, a marketing development plan, technology development plan, things like that. And just wanted to also mention that we have our software.nasa.gov website, which has free NASA software. So there's different release types. There's government purpose, so you need a government contract for that. There's general purpose, which is US only, so you have to be in the United States, US and foreign, and public release. And then our open source is code.nasa.gov. And all the open source software requires software usage agreement, but it's free to apply, so you can go on and go to the different categories and use the same search function as before. And here are just some quick links on the technology transfer program. We have our main website where you can find everything, technology.nasa.gov, and then how to license the technology at technology.nasa.gov/license. You got our patents, our free software. SBIR, that's more for if the government has solicitations for something that needs to get done, you can go there, see if your company can fulfill that need. And then our success stories, how I mentioned off in the beginning, and then NASA Home and City, it's just cool virtualization or virtual reality kind of way of seeing how NASA affects your daily life. And again, my name is Jay Singh. I'm the Technology Portfolio Manager here at NASA Ames, and then Kimberly Hines is our Technology Transfer Office Chief. And before I let you go, just one question, that we wanted to ask is, what is left undone for your company that you might search NASA technology for a solution? So thank you again, everybody who attended. And after this presentation ends, you will be directed to the technology.nasa.gov website. Thank you so much.